SQL row source generation. The row source generation receives an optimal execution plan from the optimizer, okay, and produces a iterative execution plan that is usable by the rest of the database for executing the SQL statements. The execution plan takes the form of a combination of individual steps. Each of the steps return a set of rows, okay, and are referred to as row sources. A row source is a row set returned by a step in an execution plan, along with additional control structures so that the server can iteratively process the rows one at a time. The row sources can be a table at the most fundamental level. They can be views, okay, which eventually have to take the data from tables, or the result of a join or a grouping operation. The row source generator produces a row source tree, which is a collection of row sources that are executed in a particular order, and we can view it as a tree structure. Okay, so this is an example of a select statement similar to some of the ones we've done already in the previous chapters. We're joining, in this case, joining the employee table to the department to the jobs table. It's an equal join between the employees table and the department table based on the department ID in both tables. It's also an equal join between the employees table and the jobs table based on the job ID. And then these two form the join condition. Then we have an additional filter on it, where we're looking for employees with a last name beginning with A. And it builds an execution plan which we show in a text as an indented statement, which is just a way of expressing the particular tree structure. And we'll show you in a little bit how to relate the two together. And essentially what we need to do is we execute the most deeply indented thing first, generally, and then back up from the bottom up when we're actually reading them. Okay, so it will show us when we have a look at the explain plan, and we'll look at a number of ways of looking at them. We showed you a simple one earlier on using SQL Plus and AutoTrace. We use TKProf as another way of getting the execution plans and the row sources. So during the execution of the SQL engine, okay, it executes each row source in the tree to produce it. So we can express it as a tree structure. And there are some unary operators, there are binary operators, and there's some things that take more n-tuple operators, but a join is a binary operator. It takes two row sources and join them together. So in this case, and the order we do them in is does the left side as the driving, and then the right joins it to the right side, which would be step 6. And we just identified these with different step numbers. So this one up here has a 2 on it, a 1 on it at the top, a 2. It's represented as a tree structure where the root is at the top and the leaves are the bottom. I always joke, computer scientists are upside down in their trees. So we grow them backwards. It just makes it easier to represent them as we draw them, you know, from the top down. When we actually execute these, we go from the bottom up in a particular order. So to do the hash join, we have to do the two sides first, and the two sides have other things that need to be done. So the first hash join, its left side is another hash join. Before we can do this piece, step 6, we have to do the left side first. To do this, we have to do a hash join. It has a left and right side. We have to do a full table scan of the jobs table. Then we take each row as we read through them one at a time, and we join them by using a hash join and using an index on the other side. So on this side, on the jobs table, we build a hash table, and then we use the index to pull rows to probe the hash table. And it will allow us to join the rows together. To use the index at the bottom, we're doing the index range scan, and it returns 0 or a 1 or a group of row IDs. Okay, and it feeds the access of the table using the row IDs. Okay, so build a hash table, use an index to get a set of rows and go through them one at a time and probe the hash table. Return the join rows one at a time and then join it with the departments table. And we're doing a full table scan of the department, and we're going to build a hash. Once we join this table, we produce this intermediate table, because it's really the join of these two. We'll build a hash table on it and use this one to probe it, okay, as we process it. So the execution tree shows you the flow of the row sources from one to the other. When you read it from the bottom up. Basically, you go down the left-hand side until you get to a leaf. The leaf are the ones in black at the bottom, on the very bottom. They're the very bottom of the tree. So we go down the left side. So we do this first, feed it to the hash join, but before we complete it, we have to go down this, do 4, do 3, do the hash join of candidate rows, and then we need to do this, but before we can do this, we need to do the right-hand side. So process the right-hand side. So you read them from the top up, but in a particular order, the way it executes them, okay? So we also saw that we listed the row sources in the execution plan. So we have a little quiz, okay? And the little quiz asks us a blank question. The blank step involves separating the pieces of the SQL statement into data structures that can be processed by other routines like the optimizer. Okay, and I gave them an actual name. I called them query block. So we'll let you contemplate that for a few moments. Okay, and then we'll review the answers. So the answer for this one is A, the parsing. The first phase we do, we need to semantically check it, syntax check it, check the privileges. If that's successful, we build it into query blocks, which are our data structure the optimizer can use to decide on the best execution plan. And then the best execution plan is fed to the row source generator, and then we finally execute. So it was in the order of the way we process it, but the very first phase when we do the initial parsing. And don't forget, the parsing can do a soft parse to look it up in memory and discover we already have an execution, or it could have to build the execution plan, which is where the optimizer and the row source. But in the first phase of doing the initial processing of the statement, we build it into individual structures that can be processed independently. The row block, the SQL blocks, statement blocks. Okay. Next up is the statement generation, and this was an example. And I'm having trouble with these slides. I'm going to remember to hit the right-hand button. So the next topic is we have an interesting little question. Why do we need an optimizer? Okay, well, the reason why is that there are certain decisions need to be made. So we've got a query that needs to be optimized. This is a query block. It's a standalone statement or as a query block. Select star from employees where job equals manager. Okay. Now the question becomes, the optimizer asks itself, or somebody needs to ask, is how to retrieve the rows. And we need to know how many of the employees actually hold the job role of managers. Okay. And what will give us the information about that, okay, is we need the schema information, the fact that we have a table, And if on the table we have an index on the jobs, it may be a particular access path. If the index isn't usable, it can always do a full table scan of an employee table or any table to solve a query. So as long as we have one index, then we have a choice, full table scan or index lookup. So we have to ask how to retrieve it, check to see what are the possible access paths. We discover we have two of them. Which of the two, using an index or using a full table scan to read every row and every block, is better? And the answer is it depends on how many employees are managers. So we use statistics on the tables and indexes to get indication. We want to know how selective is the job. In other words, what are the percentage of managers? If there are very few number of managers in the organization, in this case they are indicating there's 1% of the employees are managers, then returning 1% of the employees through an index is a good access path. We're returning a small number of rows, use an index to access it. Okay, so it looks at the two with the statistics and says, few employees, let's do an index. I have a plan. Okay, so it made a decision on whether to do a full table scan or an index. Somebody has to make the decision. Another case, it could be on a different database for a different company. It could be the company's changed over the years. Okay, we have the same query to optimize. How should I retrieve it? We check the schema, we come up with the same two possible access paths. An index in the little pyramid is our way of symbolizing an index. And then a full table scan. Okay, which one is faster? Consult the statistics. Now for this company, it appears to be management heavy. 80% of the employees are managers. Okay. In that case, an index is not the best execution plan. If we're going to get the majority of the rows, even 25% of the rows, in all probability, if everything else was equal, which it never is in reality, but if it was, then we should use a full table scan. Indexes are inefficient once you have to return a large number of rows. It just gets an inefficient structure. So it says lots of employees, 80% are managers, let's do a full table scan. So the optimizer makes decisions based on its input. It uses the statement as an input. It uses the schema information, what indexes are out there to define the access paths. We can either use one or more indexes, or we could always do a full table scan. And it uses the statistics on the tables and indexes to get an understanding of the distribution of data in this case. It also gives it other information. As long as we give it good statistics, current up-to-date schema information, and a reasonably well-written SQL statement, it should be able to come up with an execution plan. Remember, how we write the SQL can influence the execution. If we wrap the job column with some function call, it will prevent it from using the index. And we saw that in lesson 4. So the components of the optimizer. Okay, we take the SQL statement as part of the initial transforming. It's parsed into query blocks. Okay, then the optimizer goes to work. And then, of course, as part of that initial processing, we syntax, semantics, and check the privileges. If everything checks out, then we pass a query block to the optimizer and tells it to optimize it. And the first thing it will do, that quite often it can find an equivalent way of restating the statement that may lead to additional execution plans, and we call those query transforms. There are a large number it can actually try. We're going to look at a few of them later on in this lesson. Certainly not all of them, but a few of them. So it will try some transforms. Okay, each of the transforms is sent to an estimator that uses the statistics we store in the data dictionary to cost the plan. Okay, and the optimizer will pick the lowest cost plan to use. It will try all the possible permutations and different access paths. If it's joining, it will look at join order, join methods, cost out all the different ways of doing it, and select the lowest cost method to use for generating the execution plan, which will generate the row sources that give us the execution plan. That plan gets placed into shared pools so we can share it with many processes. Do the expensive processing once and share it with others. Next up are the query transforms. So we wanted to give you a little overview, certainly not all of them. We'll look at a few of them to give you an idea how they work. Okay, so the optimizer decides what are the available query transforms. Okay, sometimes it can get an advantage by rewriting the original statement into a semantically equivalent statement that can produce the same results a different way, and that may lead to a lower cost execution plan. So there are a number of possible transformations. Well, they talk about the OR expansion. If we do it as a OR with a group of equality predicates, we can't use an index. If we ANDed them together, we could use an index. There are cases that we can rewrite it so it's expressed with an AND instead of an OR to give us the same information. Another way is doing the subquery on nesting, taking it as a subquery and rewriting it either as a regular join or as a join to an inline view. Another one is we introduce complex view merging for more complex views. For simple views, we can merge them. In some distinct cases, they can do complex view merging. Join predicate pushdown. And we notice that they use some interesting little short forms. And when we talk about later how you can get a 153 trace from the database, what it will do is this dump actually dumps all the decisions the optimizer made and all the transforms it looked at as part of looking at different execution plans and why it didn't use it. Some of them are rejected because they were higher cost than a plan it already found. Some of them are rejected because conditions that ensure it gives you the same results weren't met. They're just not possible to use certain transforms in some cases. And these are the short forms that they use on that report. It actually gives you the summary of all of them, and there's a lot more than we talk about. There's one called transitive closure. Another one is a in list can be converted to an exist statement. And the exist statements are executed as semi-joins. And not in can be converted to a not exist that are treated as anti-joins. We also talk about filter pushdowns. There's a group more on the bottom of your page, and even that doesn't touch all of them in reality. If you're interested in them, they're documented in the documentation for the SQL tuning in 12C. So now we're going to look at a few of these transforms. First one up is the OR expansion. If we express this query, select star from employees, where job equals clerk or department equals 10, if we have an OR condition, even though we have indexes on the job table in the department, it can't use them. It will do a full table scan and apply these two predicates to each of the rows. It has to get each block into memory and check each row in each block. Doesn't know if there's 0, 1, or 50, whether they occur at the beginning, the middle, or at the end. It's got to check everything. It can do the same statement can be rewritten with a transform that gives us the same results. We do it as a union all, so we avoid the sort because each of them gives us a subset that are going to be unique because we remove the duplication from one leg. So we can express it as the first part of the query as one side of the union, select star from employees where job equals clerk. Because there's no and on here, we now open up the possibility of using the index on the job table. Then we union it all with the second part, which is we want to use this predicate, select star from employees where the department equals 10, not job, department equals 10. Okay, and we're going to end it with another piece that is intended to remove the duplicates. Okay, and we don't want them to have the role of clerk, because any of the clerks we already got from this, and this wouldn't return duplicates, so we need to make sure this doesn't, and we want to avoid a big sort if these were big tables. Okay, so we do the department number equals 10 and job not equals clerk. It can now use the index to get this portion because we're anding it with something, another predicate. Okay, we're not anding it, we're not oring it, so it can use this index. So we transformed what was a or into a union with an and condition. On one side didn't have any additional except when we pulled up. It can use this index. There could be an index on the job column, but generally, if there's a reasonable number of jobs, we found that when we looked at the indexes, if we wanted everything but clerk, we did it with employee ID, which was a more extreme case. But if there's lots of different jobs, doing a not statement generally won't use the index on it. So we now opened up the index. Which one is better really depends on your data generally. If it is a very small employee table, maybe just doing a full table scan and checking each row is a good idea. If the employee table is very large, maybe doing two queries essentially, okay, but using the indexes may be faster than doing the full table scan, especially if these are very selective. There's only a few people in Department 10 and there's only a relatively few clerks. Then using the indexes to find the data instead of one big full table scan may be faster. Who makes the decision? The optimizer. It costs out both possibilities and goes what it perceives as the lowest cost. As long as the statistics are up to date on our objects, it should make good decisions for us. Okay, next one is having a look at subquery on nesting. We have the original query, select star from accounts, where the customer number is coming from an in list, and the in list is just another select. Select the customer number from the customer's table. This is a non-correlated query. We're taking a bunch of customer numbers and feeding it to the outer one. So to execute this, get our list of customer numbers and feed it to the outer one. It can be transformed to a join. Okay, we can join the account table, which are outer one, to our customer table, which is our inner one, and we can express it as an equal join. We only want to get the accounts for the customers that are valid customers. So do an equal join based on the customer numbers to return the accounts. But in this case, it would return just all the row columns from the account table. So we do it here by just specifying the table name, star to say we only want the information from the accounts. Usually, we wouldn't use star in the application. It would have a subset of the rows. Makes it easier for us to write the SQL, faster to write generally. And usually the customer table, the customer number is the primary key. we now opened up an index that we could use with their join. When we do these, both of them are done as full table scans essentially. Okay, interesting.